After this lesson, students will be able to solve and graph one-step linear inequalities. Do now. Try these 4 questions on your own, so pause the movie and resume when you're ready. Number 1. We are solving this equation, 5x minus 7 equals negative 12, for x. When we're solving for a variable, we need to isolate x. In other words, we need to get rid of anything else that is going on to that x, such as subtracting 7 or multiplying by 5. Now in algebra, when solving for a variable, we need to be like detectives and work our way backwards to figure out what x is. And because of that, we need to use the opposite of the order of operations, or the reverse of PEMDAS. So while we would normally multiply first and then subtract after, in algebra, when solving for x, I need to first get rid of the negative 7 and then get rid of our 5. Now in order to get rid of negative 7, I could add 7, which would make it equal to 0. Whatever I do to the left side of the equal sign, I need to do to the right side. We can think of an equation as like a balance or a scale. One side equals the other side, so our scale is balanced. I can do whatever I want to either side as long as I do the exact same thing, so that it remains equal. Now on the left, when I have negative 7 and I add 7 to it, then that turns into 0. Negative 7 plus 7 is 0. So on the left side of the equal sign, I have 5x. On the right side, negative 12 plus 7, different signs, so I subtract and take the sign of the higher number, gives me negative 5. Now, I need to continue to isolate my x. X is being multiplied by 5. The inverse operation of multiplication is division, so I divide both sides by 5. Now this is helpful because 5 divided by 5 is 1, and 1x is the same thing as writing x. Negative 5 divided by 5 is equal to negative 1. So now I've isolated my x and found that x equals negative 1. Now it's always a good idea to check your answers. So, in order to check my answers, I'm going to plug in negative 1 for x into the original equation and see if it makes this equation true. So 5 times negative 1 minus 7 equals negative 12. Negative 5 minus 7 equals negative 12. Same sign, so I add and keep, and I get that negative 12 equals negative 12, which is true. So I know that x does equal negative 1. Number 2. 6 equals 3 minus x. I can think of this as 3 minus 1x. Now technically, I am multiplying negative 1 times x and adding 3. A lot of students get confused and think that 3 is being subtracted and that therefore you would add 3 to both sides. If it helps you to visualize this, you can change the order of the terms, but make sure that you keep the sign with the term. We have positive 3 and we have negative 1x. So if I were to rearrange this, I could write it as 6 equals negative 1x plus 3. This may help you to see better that we are adding 3, and that therefore in order to get rid of the 3, I would subtract 3 from both sides. Positive 3 and negative 3 cancel out, so I'm left with 3 equals negative 1x. Negative 1 is being multiplied to the x, so I can divide both sides by negative 1, since division is the inverse operation of multiplication. Negative 1 divided by negative 1 is 1. 1x just gives us x. 3 divided by negative 1 is negative 3. So my final answer, I have that x equals negative 3. Now I can check this by plugging in negative 3 for x into our original equation. 6 equals 3 minus x, which is negative 3, and 3 minus negative 3 is the same as 3 plus 3. 6 does equal 6, so our answer is x equals negative 3. Now for number 3, x divided by 4 equals 12. Since the inverse operation of dividing is multiplying, I'm going to multiply both sides of the equal sign by 4. I can think of this as 4 over 1 and cross-reduce. And now you see why it's important to use our inverse operation, because we did cancel out our 4 and we're left with x, which was our goal, to isolate x. On the right side, I have 12 times 4, which is 48. So x should equal 48, but I do need to check to be sure. So I plug in 48 for x in our original equation, and 48 divided by 4 is 12. 12 equals 12, so x equals 48. Finally, we have 8x equals negative 32. Since I'm multiplying by 8, I can divide both sides by 8, the inverse. The 8's cancel out because 8 divided by 8 is 1, and 1x is the same as x. And I have negative 32 divided by 8, which is negative 4. So x equals negative 4. To check our answer, I can plug in negative 4 for x, and I get that negative 32 equals negative 32. So x does equal negative 4. Now today's lesson is all about inequalities. An inequality is a sentence formed when an inequality symbol, like less than, greater than, less than or equal to, or greater than or equal to, is placed between two expressions. So for example, negative 9 is less than negative 8 is an inequality. X is greater than 10 is an inequality, or 4x plus 2 is greater than or equal to x plus 11, which is also an inequality. Notice how these do not have equal signs. Therefore, they are not equations. They are called inequalities. Now, when we graph a linear inequality in one variable, we're essentially graphing or shading all of the set of points on a number line that represent the possible solutions of the inequality. A solution is a number that when you plug it in for your variable, such as x, it makes the statement true. So for example, if I have that x is less than 2, x can be all real numbers that are less than 2, meaning x could be a half, since that's less than 2, x could be 0, since that's less than 2, or x could be negative 5,000, since that's less than 2. You'll notice that there are in fact an infinite number of solutions for x. So, to graph this, we take our number line. Now x is less than 2, so I start at 2, and I put an open circle. I'm not coloring it in, because I'm shading all of the solutions, or numbers that make it true. And if I were to plug in 2, 2 is not less than 2, and therefore I'm not allowed to color this in. That does not demonstrate a solution. So now, I need to figure out which side I can shade. Well, x can be any number less than 2. It can be 1, 0, negative 1, negative 2, negative 3, or any of the numbers in between, or even less than negative 3. So I'm going to go and shade all of these numbers and the arrow, which shows that the solutions do go on forever in that direction. Anything that's shaded on my number line, I can take and plug into my inequality, and it will give me a true statement. Number 2, when I have x is greater than negative 2, I go to negative 2. I'm going to put an open circle again, since negative 2 is not actually greater than negative 2, and therefore does not make this statement true. But x can be any number that is greater than negative 2. So negative 1, 0, 1, 2, 3, anything greater than 3, all these fractions and decimals here that are shaded will also make this statement true. A quick hint if you're having trouble figuring out which way to shade is sometimes I'll look at the inequality symbol, less than, and think of it as an arrow. And that helps me to remember which direction I need to shade in. Now when I have an inequality x is less than or equal to 1, this time 1 is less than or equal to 1. Since 1 makes this statement true, I'm going to color in the circle on 1, making it a solid circle. And x can be any number that is less than or equal to 1, so I shade all the numbers that are less than or equal to 1. And then we have x is greater than or equal to 0. This does include 0 since 0 makes the statement true. And any number that is greater than or equal to 0 is also going to make our statement true and therefore should be shaded. So in summary, when graphing linear inequalities in one variable, you need to start by plotting an open or solid dot. Less than or greater than have open dots, which show that the number is not included in our solution set and does not make the statement true, while less than or equal to and greater than or equal to have a solid dot, which shows that that number is included in the solution set and makes the statement true. Then you darken the part of the number line that are solutions of the inequality. Sometimes you'll be given an inequality and asked if a specific number is a solution of the inequality, which means when you plug in the number, does it make it true or false? Well, for number 1, we have x is greater than -8, and they want to know if 3 is a solution of the inequality. Well, when I plug in 3 is greater than -8, and therefore 3 is a solution of the inequality. Number 2, I plug in 2 for b. Since 0.2 is not greater than 2, 2 is not a solution of the inequality. You try numbers 3 through 5 on your own. Pause the screen and resume when you're ready. Number 3. -0.5, when substituted for g, makes a true statement, since -half is less than 9, and therefore it is a solution of the inequality. Number 4. When I substitute 5 in for m, I get a statement that is not true. 5 is not greater than or equal to 5.4, and therefore 5 is not a solution of the inequality. And finally, 19 is less than or equal to 19, and therefore is a solution of the inequality. You try these 3 on its own. Notice how each question has 2 parts, part A and part B. So state whether each part is a solution of that given inequality. Pause the movie and resume when you're ready. Number 1. 5x minus 7 is greater than -3. Well, we want to know if 0 is a solution. So we plug in 0 for x and see if it gives us a true or false statement. I get that -7 is greater than -3. This is false, and therefore 0 is not a solution of the inequality. Part B, I plug in -1 for x, and I get that -5 minus 7 is greater than -3, or -12 is greater than -3, which is false. And therefore, -1 is not a solution of the inequality. Number 2. -3 gets plugged in for v, I follow the order of operations to simplify, and I get that negative 17 is less than or equal to 4, which is true, and therefore negative 3 is a solution of the inequality. Now for negative half. Well, half of 9 is 4.5, and since they're different signs, or unlike signs, I'm going to have a negative answer after multiplying. So 9 times negative half is negative 4.5, plus 10 is less than or equal to 4. And now I subtract, because they are different signs. And I take the sign of the higher number, which is positive. 5.5 is not less than or equal to 4, and therefore negative half is not a solution. Number 3. We plug in 2 for n. In this case, we plug it into 2 separate locations. Now when simplifying with the fraction, we simplify our numerator, then our denominator, and then we divide or reduce. So I start with 6 minus 2, which is 4, over 2. And 4 over 2 is the same as 4 divided by 2, or 2. Now 2 is not greater than 8, and therefore 2 is not a solution of our inequality. And finally, negative 3. 6 minus negative 3 is the same as 6 plus 3 over n, which is negative 3 when we substitute it in. I simplify my numerator, which is 9 divided by negative 3. And 9 divided by negative 3 is negative 3. Negative 3 is not greater than 8, and therefore this is not a solution of the inequality. Now I'd like you to try graphing each of these inequalities. So fill in a number line. Make sure you have a few numbers greater than the number given and less than the number given, and then determine whether or not you have an open or closed circle and which side to shade. So pause the movie and try these on your own, and resume when you're ready. Number 1, x is greater than 4. So I know I'm going to have 4 involved in my number line, so I'm going to put that in the middle. And then I'm going to create equal intervals on my number line going in both directions. In this case, my scale is going to be 1. And I try to make these intervals as equal as possible. Now, since x is greater than 4, I have an open circle on the 4, and I'm shading any numbers that are greater than 4. And I also shade in the arrow to show that these solutions do go on forever in that direction. Number 2. I start with negative 2. And I fill in the scale on my number line. Now p is less than negative 2. So I have an open circle, since negative 2 is not less than negative 2. And then I'm going to shade the numbers that are less than negative 2, including the arrow. Number 3. Notice how our variable is written on the right side. Now when you plug in numbers, you'll notice that the trick of using our arrow is not going to work when our variable's on the right. Here's why. If I put negative 5 and create my number line, I know it's going to be a solid circle on -5. But now when I determine which side to shade, I need to figure out what are numbers that when I substitute them in for B, that it'll make this statement true. Well, normally you would think, oh, I'll shade to the right. So for example, -4 would be shaded. But if you were to substitute -4 here, -5 is not greater than or equal to -4. Instead, when I see the variable on the right, I like to flip this entire inequality symbol around, and then the trick does work. B is less than or equal to -5. So I'm going to shade numbers to the left of -5. And now the direction that I'm shading, left, does match our inequality symbol. So feel free when you see the variable on the right to begin by flipping the entire inequality around before you start graphing. So now for number 4, that's what I'm going to do. I'm going to change this to C is greater than 10. I'm going to put 10 on my number line, create my scale, now C is greater than 10, so it does not include 10, so I have an open circle, and now I'm shading to the right, which are the numbers that are greater than 10. And finally, number 5, k is greater than or equal to -1. I create my number line. On -1, I have a solid circle since -1 is greater than or equal to -1. And I shade all the numbers that are greater than or equal to -1. So I shade to the right. Now let's practice when we have addition and subtraction involved in our inequalities. Now before I can graph these solutions, I need to make sure that my x is isolated. To isolate x, we solve for the variable in the same fashion that we would if this were an equation, using inverse operations in the reverse order of PEMDAS. So if I have x plus 8 is greater than or equal to 1, I need to get rid of this plus 8. In order to do that, I do the inverse of adding 8, which would be subtracting 8 from both sides of the inequality symbol. This cancels out, so I'm left with x is greater than or equal to -7. Now I can go ahead and graph my solution. So I create a number line where I have -7 and a few numbers to the left and to the right of it. Since it's greater than or equal to, I put a solid circle on -7, and I'm shading anything that is greater than or equal to -7. Now number 2. Notice how our variable is on the right side of our inequality symbol. I like to switch this around, as I mentioned before. So m minus 5, which is what I have on the right side, is greater than 3. Notice how my inequality symbol does flip when I flip my inequality around. Now, I can get my m on its own by adding 5 to both sides. This cancels out, so m is greater than 8. I can go ahead and graph my number line where 8 is in the middle, and I have a couple of numbers to the right and to the left of 8. 8 is not included since 8 is not greater than 8. So I have an open circle, and I'm shading to the right. Number 3. Try this on your own, and also try number 4 on your own. So pause the movie and resume when you're ready. Number 3, I have 5 plus x is less than or equal to 3. If you'd like, you can change the order of these terms so that you have positive x plus 5 is less than or equal to 3. And that may help you visualize better that you are adding 5 and therefore need to subtract 5 from both sides of the inequality. So I have x is less than or equal to negative 2. Now I can create my number line with negative 2 in the middle. Negative 2 is a solution, so I have a solid circle, and I shade everything that is less than or equal to negative 2. And now for number 4. This time, I'll start by not flipping it around so you can see it both ways. So instead, I'm just going to add 2 to both sides first. So I have 5 is greater than m. And at this point, I can flip everything around to get that m is less than 5. I draw my number line. Five is not a solution, so I have an open circle, and I'm shading to the left. Now multiplication and division is very similar. However, there is one very special circumstance that you need to keep track of where you have to actually reverse the inequality symbol in order to maintain a true statement. And that circumstance is when you multiply or divide both sides by a negative number. So, let's do a few examples. Number 1, we have a divided by 3 is greater than 12. Just like as if this was an equation, I get rid of dividing by 3 by multiplying both sides of the equation by 3, or 3 over 1. And I'm left with a is greater than 36. Now to save time, we won't graph these since it didn't specify, but you should be able to graph a is greater than 36. Now number 2, I'm multiplying b by 7, so I divide both sides by 7. I get b is less than negative 9, which I should be able to graph if I was asked to. Now notice how on this one, we did negative 63 divided by 7 and got a negative answer, but that does not fall under this category since we did not divide both sides by a negative number. We divided both sides by a positive number and just got a negative answer. So we did not have to flip our inequality symbol. However, for number 3, since I'm multiplying by negative 7, the inverse would be to divide by negative 7. This time, I am dividing both sides by a negative number. So, instead of writing less than, I now flip the sign to be greater than, and I get that b is greater than negative 9. So you have to be very careful because it is easy to make careless errors on quizzes and tests when you forget about flipping your inequality symbol in these situations. And finally, number 4, we can multiply both sides by 5. to get that W is greater than or equal to 150. You try these two questions, so pause the movie and resume when you're ready. Number 1, instead of dividing by 2, we're going to multiply both sides by 2 in order to cancel that out. And I get that P is less than or equal to -4. I did not need to flip my inequality symbol since I multiplied both sides by a positive number. If I were asked to graph this, I'd put -4 in the middle and a couple of numbers on either side of my number line. I'd have a solid circle on -4, and I'd shade to the left since I'm looking for numbers. Since I'm looking for numbers that are less than or equal to -4. Now for number 2. Which two inequalities have the same solution? So we're going to simplify each of these 3 parts in order to figure out which two have the same solution set. For part A, in order to get rid of dividing by 5, we multiply both sides by 5. And we get that n is greater than -10. I did not need to flip my inequality symbol. Now for part B, I have to divide both sides by -2. Since I'm dividing by a negative, I do need to flip my inequality symbol, which I didn't write down. So I now have greater than -10. So already I see that these two inequalities have the same solution. But let's double check now with part C and see what we get. This is like saying -1n divided by 2 is less than -5. I start by multiplying both sides by 2. And I have -1n is less than -10. Now -1n is like -1 times n. So instead of multiplying by -1, I do the inverse, which is dividing both sides by -1. And when I divide by a negative, I have to flip my inequality symbol. So instead of less than, I have greater than. But -10 divided by -1 gives us +10. So the two inequalities that have the same solution are A and B.